Okay, so today is a continuation of our discussion on the LLL lattice reduction algorithm, and we'll be focusing on the swap condition, the Lovász condition that we briefly talked about last time, but we haven't dived into the details and we haven't explained the intuition and also more concretely why Lovász condition is designed in such a way that is slightly different from the Lagrange swapping conditions in dimension 2. So let's start with dimension 2. We know last time that I think we have seen many times now that the Lagrange reduction in dimension 2 works something like this. You have B1 and B2 start with. You first size reduce it. You have a size reduction steps that brings the B2 to its orthogonal, the GS orthogonal vectors close to that, such that the length after the reduction, the B2 prime, is, so the B2 prime is within half of B1, and it's usually within the range of minus half of B1 and half of B1, right? So it can be bring very close to this, to the orthogonal projection of B2. Okay, so you first size reduce it, and the Lagrange reduction says the swapping steps, right? So swap if the length of B2 prime is smaller than B1. Okay, so this is the condition. This is the swapping conditions for Lagrange reduction. And here the idea is that if B2 prime turns out to be very short, let's say this is B2 prime, after the reduction is very short compared to, say, B1. Okay, B2 can start it off very, very long, but after the reduction, it turns out to be very short. In that case, there's further reduction opportunities, right? So for more opportunities to reduce the B1 even further. And as we can see intuitively, if B2 prime is very small, right? And if I size reduce it, so that this is the orthogonal projection of B1 onto the orthogonal supplement of B2 prime, the reduced one. So if you bring it close to this, then B1 prime is also going to be reduced. Okay, so there's further opportunities. So that's the kind of refreshing on our memory about the Lagrange reduction. Okay, so now let's go recall last time in dimension N, okay, dimension D. So say that the LLL accept some basis factor, and that this basis factor, basis vectors, and this basis vectors is defined as B1 to BD, and D is the dimension. Okay, and each BI belongs to, we're just dealing with integer lattices for simplicities. In practice, we're usually dealing with rational integers, but you can scale it up so that every entry is an integer. So each one has an embedding degree of n, but there are D dimension. Okay, so let's recall. Last time we talked about the QR factorization of this B, where we say that B, any B, where the BI to BD, if they are linearly independent, then you can factor it out into Q components, where Q is an orthonormal vector, a matrix, and R is the upper triangular So the R looks like this is 0, and this is R1 to RDD, right? And there's some off-diagonal matrix, and the Q is equals to exactly the B1 star divided. It's an orthonormal, right? So you will have to divide it by this, the length of the GS vector, the Gram-Schmidt vector. So BD divided by the length of BD. So this is how Q looks like, and we talk about how the R matrix looks like last time, where the RII, all the diagonal matrix, all the diagonal entries, equals to the length of the orthogonal vectors, right? During the GSO. So basically, this is the GSO orthogonal vector, right? Orthogonal vectors, whereas any off-diagonal matrix, ij, for example, this one, ij, right? The relationship was this, was the GSO coefficient, ij, times what? The length of the GSO orthogonal vectors. Okay, so that's kind of a refresher. And now let's refresh what does the swapping condition looks like in dimension n in LLL algorithms. So this is the Lovász condition. Okay, what it says is, so there is this delta, which is a parameter of bi. It has to be smaller plus I plus 1, I. So, okay, so this is the Lovász condition. And just to visualize it a little better, what does it look like? So it roughly means if, let's say, we start with a very simple case, right? We start with a simple case where we only have 3 dimension. Okay. Let's say we have 3 dimension. Okay, so R11, 0, 0, R22, R33, R21, R31, R32. Okay, so if this is the R factor of this input matrix B, then what the Lovász condition is focusing on, it is focusing on this shape, these entries, and it's basically saying that delta of R22 square has to be smaller than R33 square plus R32 square. Okay, so basically you can map each term here. Again, remember that, sorry, there is a missing square over here. You can map each term. Remember this Rij is the GS coefficient times the, the length of the respective orthogonal vectors. So this is basically intuitively how you think about it. So if let's say, if lambda equals to 1, what you can simplify, sorry, the delta equals to 1, you can simplify this into, I want, this to be longer than this. And just to remind you, we know that the length of B2 is equal to R22 square times plus R21 square, and the length of B3 is R33 square times plus 32 square plus 31 square. Okay. So, and this can be easily seen if you see the QR dimension, the QR factorization, right? So yeah, I won't repeat it. I think we covered this last time, but just to refresh, this is the Lovász condition. Now, if we manipulate this a little bit better, because this is just looking at this formula, it's not very intelligible of what this is really doing. I give the intuition by giving you this dimension 3 examples, but if we were to rearrange the terms a little bit, we can see that what this is saying is the BI, the Gram-Schmidt vector length, has to be smaller than times the next. Okay, and usually what's the range of this delta? This range of the delta is usually exclusive of 1/4 and inclusive of 1. Okay, so now we know, because of size reduction, right? Because of size reduction, we know that the ui plus 1 I square is smaller than 1/4, right? Because we know that the size reduction step is basically bringing these off-diagonal entries closer to the diagonal entries, and so that the coefficient is smaller than 1/2, and their square is, smaller than 1/4. Okay, so if we were to expand this further, so we know that this is going to be smaller than this expression, and we just map this term into another, for convenience's sake, into another term called alpha. Okay, so essentially we can interpret the Lovász condition as the following statements. Basically, is smaller than alpha. Now, in the original paper, the Lenstra, and Lovász, they chose delta to be 3/4, such that alpha equals to 2. That makes powers of 2 and things like that slightly nicer to look at. But now you get the idea where does this power of 2 comes from. It's really dependent on the choice of the delta. But essentially, if we're looking at this expression, this is basically saying that the length of the GS orthogonal vectors at I has to be smaller, and there shouldn't be any drastic jump. So the alpha could be bigger than 1, right? So alpha is usually bigger than 1. So what is intuitively what it's saying is the Gram-Schmidt vectors doesn't drop too sharp, okay? Doesn't drop too fast, okay? Right. So if, let's say, the BI plus 1 is dropping too fast, sorry, the orthogonal, the star, the BI plus 1 star is too small, then the Lovász condition will be violated. And when the Lovász condition is violated, you need to swap it and then do a size reduction again. Okay, so the Lovász conditions ensure that the orthogonal vectors of the reduced spaces won't drop too fast. So that's the intuitive interpretation. We briefly explain how do we understand this drop too fast thing. Why doesn't we want these orthogonal vectors to drop too fast? Well, the idea is that if, let's say this is I prime, if we drop too fast, say this is the BI plus 1, and we know because of the size reduction, the actual BI plus 1 is probably somewhere in the vicinity of this BI plus 1, the orthogonal vectors, right? If this is short and it drops very quickly compared to the previous orthogonal ones, and we don't know exactly where BI is, but again, it should be in the vicinity of BI. Sorry, it's orthogonal vectors. Now, if BI plus 1 star is, significantly smaller than BI star, the previous orthogonal vectors, then there's opportunities to further reduce it. As you can see, if we swap and then reduce again, it will be similar to the previous case. It will be the previous case because this one is short, so you can bring it closer to this, where this is the BI prime. Okay, so and this BI prime is going to be shorter than the BI, so there's more opportunity to further reduce, and that's why when Lovász conditions, that's like a very direct interpretation of the Lovász condition. Okay, with that, let's go through. So we know that if we go through the so-called LLL reduced basis, if we have reduced basis, then we know that first of all, it's size reduced, which means that all the the GSO coefficient is smaller than 1/2. I mean, the absolute value is smaller than 1/2, and also the Lovász conditions is satisfied. Okay, this is what it means to be LLL reduced, and this will also be the output of LLL algorithms. So it will guarantee this. Otherwise, it will keep swapping, keep reducing until both of these conditions are met. Okay. So the next thing is I want to rederive the qualities of the first vector, the first reduced spaces after the LLL algorithms. Because last time I think I didn't do a good job explaining the theorem and deriving the theorem. So now, because we have this, okay. So now let's look at what can we derive from this. the first thing we notice is, given this, we know B1 star, which, by the way, equals to B1, okay? This is smaller than alpha times the B2 star, sorry, square. Okay, there's missing square here. And smaller than all the way to alpha D minus 1 BD star square, okay? So we know that. But the problem is, we don't know the ordering of these BI star. So as we talked about last time, if given the GSO, the Gram-Schmidt orthogonal vectors, the length of them and also the ordering of them is dependent on the ordering of the inputs. So you don't know how they are not in descending or increasing order. So what we can say is to have a worst case upper bound. And what the worst case upper bound is we could say that the first one is definitely smaller than the worst coefficient approximation factor for all I, right, equals to 1 to D. We can say this because we don't know the ordering of the value of these, but we could say that given the worst approximation factors at the front, this is definitely true. Yeah, I think this is trivial. Another way to, and this also implies that we could pick the smallest BI, although I don't know which one because I don't know the ordering, but I could say it is smaller than the minimum orthogonal vectors square. Okay. Now there is a fact that we need to use, and I will prove the fact in a little bit because it should be trivial to see. For any basis, okay, for any basis for the lattice, the minimum of BI star is smaller, shorter, or equal to the shortest vector. So this is the shortest vector of these lattices, okay, lambda 1. All right, so we have this fact, and which I'll prove. I'll get back to in a little bit. And with this fact, okay, plugging this fact, we can easily see. Let me use another color. So this is the theorem 1. Is that B1 should be smaller than, sorry, this is, all these 2 should be alpha, my bad. But in concrete choice, it can be 2, okay? But it's alpha D minus 1 divided by 2, because there is a square, so I square root on both sides. Minimum of all the orthogonal vectors, and this is smaller than. Okay, so this, sure. I keep writing 2, but this should be alpha. Okay, and this is the exponential approximation factor. This is the exponential approximation factor for the SVP. So sometimes if you read crypto papers, you will see this is some c to the n, right? C to the n, where it means that it's exponential approximation factors at the front. And okay, so that's the first theorem. So now let's go back to the fact and see why this is true. Now, to see this why this is true, let's imagine that B is formed using B1 all the way to Bn, and so let's say Bi is the minimum, has the minimum orthogonal vectors. Then the rest, okay, the rest of Bi, sorry, let's say, okay, let's give a concrete example. Let's say B4 has the smallest. So Bi, other than 4, except 4, will form a hyperplane, right? So this is basically the lattices that is formed using B1, B2, B3, B5, and all the way to Bm. Okay, so integer combination of this will form a hyperplane, and then you will have, so this is going to be the before star, and let's say this is the actual before, and the lattices is going to be a linear combination of, let's say, C times before plus this lattices, right? And it should be easy to see that the length of this would not be, because this is already the smallest one, the distance between any of these lattices point would not be smaller than this before star. And we're assuming that before star is the minimum of bi star to begin with, right? Because any of the distance will be bigger than this. Any of the points, because any points in this hyperplane, so you will have many hyperplanes, right? And this is the closest hyperplane that you would have. And any points between the two is going to be bigger than this. And any points within the plane would also have a larger distance. Because, for example, this is before and this is before prime. And the distance between before and before prime is also larger than before star. And this is because that we assume the before star is the minimum of the orthogonal vector to start with. And in order for you to get before prime from before, you need to add an integer linear combination of some of these previous basis points, where these basis points is definitely of these basis vectors, and these basis vectors their length, their norm has to be bigger than this based on our assumption. So it shouldn't be too hard to see that this fact is trivially true. All right. So that's the first theorem that we prove. Now the second theorem is we want to show, okay, is that given this, okay, now we know this, we could see the following. If we times this, if we product this like d times, right, we basically product all the left-hand side and also the right-hand side, what we ultimately get is b1 star to the power of d will be smaller than, the product of the alpha I minus 1 divided by 2. And because, again, we're taking the roots out, okay? So times bi star, okay? And so this is the product of left-hand side, and this is the product of right-hand side, okay? And since we know, and also I belongs to, so if this is the R factor, and this bi star is basically R11 to RDD, right? And we said before, the determinant of this matrix equals to the products of all these diagonal entries, and also the bi star. So you can easily imagine that the space, the fundamental parallel pipe formed by these orthogonal vectors is basically the product of these orthogonal vectors, right? So this equals to alpha d minus 1, and this is the geometric series, the volume of lambda. The lattices, okay? Because the product of these is the volume, or the volume of the fundamental parallel pipe of the lattices. Okay, so if I summarize it, it's going to be bi star, which equals to bi, by the way, is smaller than, divided the d minus 1 over d. Okay, so we've seen a relationship between the shortest vectors from, or the first reduced basis, and the determinant of this lattices. This is L. Sorry for my handwriting. Okay, and also the approximation factor is exponential in terms of the dimension, with respect to the dimension. Okay, so these are the two important properties of the LLL reduced factors. Okay. All right. Okay. So now with that, I think what we want to explore even further is this mysterious looking Lovász condition. Why is this the condition that they settle on? Why? Because this looks slightly different than the dimension 2 case in the Lagrange reduction. So we want to understand why that's the case. Okay, so now let's just go back to see again the Lagrange reduction, where we have the swapping condition was we're comparing the reduced basis bi b2 prime, right, with the length of entire thing with bi, whereas in this case we're only comparing some entries of b2. Again, the b2 is a product of these two, right? Sorry, the sum of the of these two. So you have two components. Why are we only comparing this, right? Why didn't we? So I guess the first question. Let me formulate it into a question. Okay, let me formulate it into a question. So question one. Why not compare, you know, the entire length, the entire length with, and specifically, if we want the first basis to be short, why didn't we compare, the first one to be smaller than any of the following? So what this means is that because we have a alternating steps of the reduced steps and then swaps. Okay, so before doing any swaps, what if my condition is not the Lovász condition? Instead, my condition is saying once you have a size reduced, let's say R, okay, size reduced basis whose whose R factor looks like this. Why don't I just compare, the first bi and compare with the length of any of the following, right, for j bigger than 1 and smaller than d. Okay, I just compare, I sort them, I put the smallest in front. Why shouldn't I do that? And the answer to that, because if that is the case, then it will be the most natural extension of the Lagrange reduction in dimension 2, right? That's the condition I would start using if I were to just generalize and trying to use the Lagrange reduction in dimension 2. And the answer to that is, historically, people actually try doing this. Okay, and the people who are doing this, who first do this, is Hermite, the French mathematician. So he did propose different variants that does similar to this. What he couldn't accomplish is, so again, once he size reduced, basically after size reduce, sort and put the smallest at the front, and then do it again. Okay, the problem is Hermite couldn't prove his algorithm to be polybound, right? He couldn't prove that this algorithm would terminate in polynomial number of steps. So, and nobody is able to analytically prove that, because the swapping steps in LLL is a local operation, and the effect is also somewhat local. Whereas here, because we don't know the ordering, right? So there's very little information because you are accepting arbitrary basis as an input. And now after the size reduce, you also don't know much about them, other than you know that the off-diagonal entries is close to their to the diagonal entry. But other than that, you don't know much. You don't know the ordering. And if you were just to sort globally, there's very little guarantee that it will ultimately terminate. So that's the answer. I couldn't go into the details because Hermite. So this is usually called Hermite's first reduction. Hermite also have a second reduction that had slightly even relaxed this sorting properties by working backwards. So he's starting from like dimension d, and then d minus 1, d minus 2, such that all the bi star is smaller than the orthogonal projection for all j bigger than I. Okay. Anyway, so I think we don't need to go into detail, but the idea is that Hermite has proposed several variants, but he couldn't prove any of these variants to be polynomial time bounded. Okay, poly-time bounded. So the Lovász condition, in a sense, is the first one that can provably terminate in polynomial time. Okay, so that's the answer to the first question. Why didn't we just directly compare the length in high dimension? The answer is basically, if you do that, then you don't get a, polynomial time bound, which is very nice in theory. Okay. The second question we want to ask is why slacking factor? Why the slacking factor delta, which belongs to this range? Okay. And let's bring back, hold on, let me see. Let's bring back this. Okay. Okay, so this is, the question is, why do we want this? Again, we said that if delta equals to 1, then it looks pretty natural, but delta could be smaller than 1, which means that I don't want it to drop too sharply, too fast, but I allow some drop. You know, if R33, which equals to, remind you again, the length of the B3 star, if the GS orthogonal vectors for B3 is slightly smaller than B2 star, that's fine. So the slacking vector allows you to have some relaxation. But why do we need this slacking factor? To understand this, we need to go to the proof that LLL is polynomial bounded, the number of swaps. Okay, so let's remind you again. Last time we talked about during swaps, you know, so we have this R. So let's say we're swapping I and I plus 1. Okay, when we swap this, if we zoomed out this little box here, it started out with, okay, let's just give an example in dimension 2 so it's easier to follow. It started off like this, and then I swap, okay, I swap, and then it becomes something like R21, R22, R11, 0. And then I will get the R factor again, right? So because after the swaps, you will have to do a size reduced, and you will get a new R factor. So what it will look like is this. This is going to be R21, R22, and this is going to be this same square value, but R11 times R22. Okay, so in a sense, this is the new R11 prime, and this is the R22 prime. Okay. All right. So what we could see is the reason why we swap is because the condition wasn't satisfied, right? So the condition is basically saying, so this is the condition. Sorry, I used 2 and 3, and here 2 and 1, so it might be a little confusing. But this condition is violated. So we know this. The reason why we swap is because it's violated. So this is the 2. Okay, and we know that the R11 prime square equals to R21 star, R22 star. Okay, so with these two, we know that R11 star is bigger R. Right. So this is what we will get when we swap with this slacking factor. And we can see if the slacking factor is 1, then there is no guarantee of progress. There's no guarantee that the new R11I is going to be smaller. Remember that last time we talked about the intuition of this swapping steps, the effect it has. It avoids sharp drop, right? So imagine this is BI and this is BI plus 1, right? So if I have a sharp dropped in their orthogonal vectors length, then I'm going to swap it, and the effects is that I'm bringing it to be slightly more balanced. So I'm reducing the swap steps would have the effect that I'm effectively reducing the new BI. So this is the BI prime, and this is the new bi plus 1 prime, right? So you're making it more balanced. This is what you do. But again, their product won't change, right? Remember, their product won't change. See, the product of here, the product R22 prime should be equals to R11 times R22, because effectively this is just a small piece out of the entire R, and the product of all of the diagonal axis is the determinant of the lattices, which is invariant. Okay, so I think this picture is somewhat, this one is somewhat important, and we will see over and over later on. So I guess here we kind of already understand why the slacking factor, because if the slacking factor is 1, then there's no guarantee. It could be, after the swap, the R11 prime, the R11 prime, stays the same. It's possible. But what I want is to reduce it. Okay? Now, on this topic, we want to see another very important fact, is that, here's the statement. The length of the B1, B1 star, which equals to B1, okay, never increase. Okay? It could stay the same, it could drop, but it never increase. To see why this is happening, and this is true throughout the execution of the LLL algorithm. Okay? To see why this is happening, so imagine this is B1, the length of B1. Okay, so for simplicity, I won't draw the norm. So we know it's talking about the norm. So this is the norm of BI. Okay, and this is B1. Okay, case 1 is B1. Let's say the B2 is the B2 star is a slight increase, and then a sharp drop. Okay, if there's a sharp drop, then I would do a swap. So there's going to be a swap, and then the effect of the swap is going to be bring down to be more balanced, right? So now it looks like this. Now there's no longer any sharp drop, so we'll be good, and we'll move forward to the rest of the basis. Okay. In this case, the BI stays the same. Okay. Stays the same. Let's see, how do I? Right? Even if, okay, and also here there's another case, like sub case within this case, is that if B2 star can be slightly smaller after the swap, or even it can start with the same as BI star, but then reduce to slightly smaller, as long as there's no sharp drop between the B1 star and the new B2 star prime, then there's no swap between the B1 star and B2 star going forward, right? So that's the first case. The second case is B1 star, and then I have a very sharp drop already. In this case, I will need to do the swap and then further reduce, which will bring it to slightly more balanced. So this will be the new, okay, so sorry for the terrible handwriting, B1 prime star, right? So B1 prime star is smaller than B1 star. So in this case, B1 star drops, decreases, okay? And let's consider case 3, where, B1 star is not dropping, slightly dropping, or even the same, or, okay? But there is a sharp drop between B2 and B3, right? In this case, if I bring down after the swap and I do the size reduce again, the new B2 prime star is smaller than the original ones, okay? But this caused a sharp drop between B1 and the new B2 prime star. In that case, I'm gonna swap these two again. So let me use a different color. I'm gonna swap these two again and bring down. In this case, B1 star also decreases. So you can go through this by yourself. You can think it through. The effects of the swaps. What does the effect that the swap have on these orthogonal vectors. Basically, the B1 star in all cases will never increase. Okay, and in some cases it will decrease. Right. So see if we after swapping, usually there's further reduction, and the further reduction brings down the length, bring down the length of some orthogonal vectors, and it could be propagating this effect all the way to B1. You could swap out the B1 to be something smaller. Okay, so I think that wraps up the second question. Okay, so now there is a third question, which is slightly more subtle and deeper in the weeds, which is what does the okay, let's start with an observation. After the reduction, after reducing everything, what does the reduced basis look like? Well, according to the floating point LLL algorithm, who the author has done a lot of empirical experiments, what they observe is that, okay, see the observation, let's see, is that I minus 1 pi, the mean value is roughly, so let's say the mean value is roughly 1.04. The mean value of the off-diagonal GSO is 0.38. Okay, how do I interpret this? Well, this means if you look at the after reduced, okay, after everything is reduced, the output of LLL algorithms, the reduced spaces, their GSO orthogonal vectors, it will look like something like it's slowly dropping. Again, Lovász doesn't allow it to drop too quickly. Slowly dropping most of the time, but sometimes it will have a large increase, which is allowed. You want it to increase actually, because if it increases, it means that the B1 is usually very short. It allows a huge. Again, let me see. This is the B. This is what it looks like. Okay, this is the dimension from 0 to D. Okay, and then it slowly drop. Okay, and maybe some increase. This could be a valid profile of the reduced spaces. The fact that the mean or the average ratio is 1.04, it means that it's most of the time, so you can interpret as decreasing slowly. And this slowly is the fact because I don't want to drop too sharply. This is governed by the delta. Okay, this is governed by the delta most of the time. Sharp increase or upticks sometimes. Yeah. So this is what the profile empirically what it would look like. Okay, and in fact, if we look at their result, this is what it looks like. Each point, the x-axis here, the x-axis is the value I plus 1 I. The y-axis is the bi minus 1 divided by bi. Okay. Right. So, well, actually, maybe it's the let me double check. Oh, sorry. So yeah, it's the other way around. Here is bi divided by minus 1. Okay. So this is going to be 1 over 1.04, which is equals to roughly 0.96. So this is going to be the mean value. 0.96 is going to be mean value, and the absolute value to be 0.38 is the mean value of these GS coefficient. Okay, this is what empirically what it looks like. Okay, now an interesting question, I guess, is if the BI are slowly decreasing a lot of the time, and we know that the size reduce is bringing BI close to bi star, then why do we know, how do we know that B1 is the shortest? All right, is the shortest in expectation. So the answer to that is you cannot really guarantee. Sometimes the output could actually be longer. But in expectation, B1 is the smallest. Okay? And we can show this. So let's give an example where B1 is not the shortest. Let's say dimension only this, 2, 0. Let's set the delta to be, let's say, 1. Okay? And in this case, let's see, maybe 0. In this case, the Lovász condition is satisfied because wait, actually, sorry. Let's say I set this to be 3/4. Okay, and so we know the 2. We can double check that 2 square, right, is 4 times 2 square is smaller than, right? So because this is this, you know, we can even say this is 0.5, right? So, right, so this is true. Lovász condition is satisfied. But in terms of absolute length, right, B1 is 2, right? Whereas B2 is 3 times 0.5 square. And apparently B2 is smaller than B1, right? And again, this is size reduced because this 0.5 is within, you know, smaller than 1, right? Half of 2. So it's both size reduced, and also the Lovász condition is satisfied. However, the output basis, the B1 is not the shortest. So this is a counterexample saying that B1 is not always the shortest. Okay, the LLL algorithm does not guarantee that. But what we could guarantee is we could say in expectation, it is expected to be the smallest. And here's, you know, we could, you know, quickly derive that. Again, let's see, R11, R22, R21. Because we know, okay, again, so R in expectation, R minus 1, RII is roughly 1.04 based on experiments. And this is roughly 0.91 something, okay? And this is roughly 0.38 in experiments. So we know B2 square, which equals to R22 square plus R21 square, is roughly, so this, using this one, is roughly 0.96 plus this value, because we, during size reduce, we bring it close enough within half of R11. So when we square it, the expectation is square times R11 square. And if you add it up, this is 1.066 R11 square, which equals to B1 star. So B2 in expectation is longer than B1. Okay? And the same thing can be said for let's say the 3-dimension case, right? The 3-dimension case where B3 square is R33 plus R32 plus R31 square. Okay, and this, because this is, you know, 2 times transitive properties, 0, 1, 4 times, you know, square and square of R11. The R32, this is bringing close enough to R22, and R22 has some relationship with R11. So this can be, if you worked out, times 0.3 square times R11, sorry, R11 square. And the last one, so again, I want to emphasize here that this is only talking about this value and this value. It does not talk about this value. This value in experiments, right? In experiments empirically, R31, or sorry, let's say the U31 is sort of uniformly random, close to uniformly random from this range. So the R32 is kind of the 31, the square is times R11 square, right? So this, in expectation, you can work out yourself, is this one. Okay, so it's just simple probability. Now, so roughly equals to this. If you add them up, this will get to 1.096 R11 square. Okay, so in expectation, the B3 is also going to be longer than B1. So again, yeah, you can do this reductively to all the subsequent vectors. So that's why, even if their orthogonal bases, so even if their orthogonal bases are slowly decreasing, it has nothing in expectation. The rate of decrease is so small, and also the actual basis is not decreasing. It could be, you know, the actual basis is usually not decreasing, usually increasing, right? That in expectation, B1 is the shortest in expectation. Okay, so that's some more subtle points that you can only understand with some experimental data. All right, so I guess that wraps up with all the intricate details of the Lovász conditions and why it makes sense in high dimensions and how does it compare with